Okay, just a quick outline. We'll go through motivation, then isotropy metrics, which is specific to this work, and then experimental setup, main results, and then additional results should we have time. Okay, so into the motivation. So first, I'll just introduce some basics about multilingual machine translation. For a lot of you, this is just review. But anyways, we just have a schematic here of a multilingual machine translation system that translates between N source languages and M target languages. And in our definition of multilingual machine translation, we're going to always be talking about complete parameter sharing. So no sort of language specific parameters. But anyways, some major benefits that are just mutually agreed upon by the community are: one, complete parameter sharing leads to a lot more just like memory efficiency. So for example, if you wanted bilingual translation models for all of these translation directions, you'd have N times N models, which is a lot, instead of just this one here. Another benefit is just improved performance of lower resource languages. So when you have all this additional signal by all the other language pairs, like for example, if you have a lower resource language that has a bunch of related languages in your training data mix, then it can get additional supervision and benefit from this sharing. And then finally, you can get zero-shot translation directions. What this refers to is, for example, if we have source language 1 into target language M, and this pair doesn't actually occur in the training data, you can still sometimes get translation performance from this pair via the multilingual model. Okay, so on the other hand, there are some limitations and performance differences as compared to the other paradigm, which is just bilingual translation models. The first one I'll mention is called off-target translation. So I just have like a tiny piece of like example code here where, so here we have the text to translate is this sentence in Igbo. It's a West African language. This sentence actually means eBay gave the book to Ogu from me. I just found it from the Igbo Wikipedia page. And then we run it through the M2M 100 model. It's a pretty famous multilingual translation model from Facebook. And we find if we want to translate into English, we basically get all the words still in Igbo. So off-target translation, I mean, sometimes it's just not even, it's neither the source or the target language. It's just a completely separate language, but it just refers to this phenomenon of not translating into the language we wanted. And then also there's this other major performance limitation called interference, which refers to not outperforming a bilingual counterpart or like additional languages in your multilingual model degrading the other languages. So here, I'll go through this. We have a model from Google from this paper from 2019 that translates 103 languages to 103 languages. And in the red here is a bilingual baseline. And these like T values, we don't have to worry about them, but these are all just multilingual translation systems with a bit of differences. Anyways, we can see here for like the highest 25 resource languages and the medium 52 resource languages, the bilingual baseline is still outperforming the multilingual counterparts, except in the lower resource setting, which it's well known that the lower resource languages are nicely helped by multilingual sharing. But as we can see, like even in sort of more current systems, bilingual baselines still can outperform for certain language pairs. And even for like current state of the art, which since then there have been bigger models with more translation directions, we don't always even get bilingual baselines. It's very expensive to run. I don't know what happened. I'll try again. Sorry, I must have touched something on accident. Okay, we're back. Sorry about that. Okay, yeah, so basically, even in current models that are even better since then, we don't get bilingual parity for some of the language pairs, and it's just like a phenomenon that occurs due to multilingual sharing. Anyways, that brings us to our motivation and research questions. So the motivation we saw in the previous slides that there are clear differences in performance patterns between bilingual and multilingual translation models, whether it's for like positive sharing or negative interference. So our major like overarching research question is, do these models differ in how they actually represent information? And to be more specific, is there a difference in the geometric structure of their internal representations? Okay, so I just said geometric structure, and now you might ask like why representational geometry to look at this problem. Before we get to the actual answer of that, we'll just talk about what kind of representational geometry we're interested in. So we're going to focus on measures of this quantity called isotropy. And basically a quick definition of it is how uniformly the variance of a data set is spread across its vector dimensions. So that's a mouthful. Just to simplify it even further. So the data set here will be our model representations. That's what we're interested in. And it's basically for the available dimensions you have for a vector, how much is the data actually using each of the dimensions. So for example, if you have like an n-dimensional vector, but only the top k dimensions actually hold any variance, then you're not actually using a lot of the available dimension. We'll talk about it more throughout the presentation. But anyways, prior work in this sort of like field of isotropy and studying geometry of language representations has shown some surprising results. I'll just summarize these couple of papers. Basically, for your favorite pre-trained model, say BERT, GPT-2, whatever, anywhere between like 1 to 10 of vector dimensions throughout the entire layers are actually being like utilized with like detectable variance. So it's sort of like less than you think. But anyways, you know, there's work on a lot of these like English-centric models, but sort of encoder, decoder, and machine translation models have been largely untouched by this sort of like geometric view. And finally, representational geometry serves as an interesting tool for our research question. And that is because a lot of these papers that talk about interference in multilingual machine translation allude to this sort of phenomenon that is not well explained called like bottlenecking or just like limited model capacity. It's not quite clear what that means and how that's actually realized in the models, but we can kind of approach this phenomenon via geometry. However, we're going to be careful not to say too much about it and link it too much to performance, because one, we're not really you know, suggesting an intervention that like specifically links the two. And two, we work with both interference settings and also smaller model settings that don't really see so much interference. But we'll just say that we're motivated by these interesting phenomenon, bottlenecking, reduced model capacity. Anyways, are there any questions so far? Okay, I'll continue. Just feel free to stop me if anything's unclear. Anyways, okay, so I'll go through like an overview schematic of our approach of what we actually want to measure to like make these comparisons. So for the same set of bytext, so we're just looking at a source language S, a target language T, and we have like n sentences. We will compute a forward pass through both our multilingual translation model in the green here and our bilingual translation model in the purple here, and collect hidden states from the output of the encoder and the output of the decoders. So we have basically for here two times the translation model types and 2 times the like module makes like 4 different sets of hidden representations we're interested in. And then we will compute the isotropy scores for each set of hiddens. And because it's the same bytext and because these models have the same internal dimension, we can compare these quantities directly. Okay, so we talked about we'll compute some sort of isotropy score, and we have some sort of vague idea what does isotropy actually mean, but now we can get into how we want to actually perform these measurements. Okay, so we have 2 metrics that we're going to focus on. The first one is called IsoScore. It's from a paper from 2022 that sort of goes along this line of, you know, isotropy and NLP models. What does it mean? And there's lots of ways you can measure it. They're proposing their best new way. But the main idea behind this metric is how far does the covariance matrix of a point cloud differ from the covariance matrix of a perfectly isotropic point cloud. And we'll go through the steps, but basically what this means is if you have variance spread across a number of dimensions, how does it compare to the variance spread across perfectly through all dimensions? That's the perfectly isotropic point cloud. So here's just like a very toy example on the right here. So this left cloud is like looking, and so basically the blue are the points the black are the principal components as defined by PCA. And if you look at the one on the left here, the variance is spread pretty equally across the two principal components here. So the IsoScore is very close to 1. It scales between 0 and 1. And on the right here, the variance is sort of localized to just like one of the principal components and not so much spread across the other one. So the IsoScore is about like 0.5 here. To go through the actual steps of it, first, you PCA reorient the data set. X here is our like model representations. And then you can compute the diagonal covariance matrix of the PCA reoriented data set. Because it's PCA reoriented, there's going to be no off-diagonal elements on the covariance matrix. It like guarantees this. So basically you just have the principal components along the diagonal that sort of tell you how much variance is captured in each of those dimensions. And then you can compute the distance between that sort of like variance quantity and the identity matrix, which sort of means that all of the variance is spread equally across the dimensions. So you kind of want to see how far is it from this like ideal isotropic scenario. And then you have this distance and basically you want to rescale it between 0 and 1. So that's fraction and directly comparable. Okay, so that's like a brief overview of IsoScore. Basically, some values that are close to 0 means that there's variance spread out only across a few dimensions, and an IsoScore close to 1 means variance is spread very equally across all of the dimensions. Okay, the next metric is called intrinsic dimensionality. So basically, the main idea behind this one, it's trying to measure something very similar to the previous metric, but in a slightly different way. This one is a little bit simpler. It asks of the true dimension D original. So that's sort of like if you have a 512 dimensional vector, this value is 512. How many dimensions can contain variance over a certain threshold? So basically, if you have a vector that's 512 dimensional and you only see variance in like 30 of these dimensions, then your intrinsic dimensionality is going to be 30 divided by 512. So on the right here, I've actually put the intrinsic dimensionalities for both of these values just to show the difference between these two metrics. So here, since it's a thresholded metric, both of these point clouds actually have ID of 1, which means that all of the dimensions available are being utilized enough. Okay, and just to go through the steps of this metric for just like more idea of what it does. So for a threshold, and this is just like set by yourself. So a common value is just 0.05. So you want to capture 95% of the variance. And for the original dimension, which is like the actual raw dimension of values, you again compute the PCA of the data set. This time we actually want to see like these like eigenvalues in this diagonal matrix here. We want to normalize them. So basically the largest eigenvalue is going to be the first one, and you divide all the eigenvalues by the first one so that they're all between 0 and 1. And then you want to see how many eigenvalues are there that are bigger than this threshold, which means they're capturing enough variance for them to be counted as a dimension that actually is containing information. So you take this sum of how many are above this threshold. Say, for example, here D original is 2, and here we actually found that both of these eigenvalues are big enough. And then we take 2 divided by 2, and we get intrinsic dimensionality of 1. Okay, so those are the metrics. Now we can get into the experimental setup. How do we actually like get these model representations that we want to compute their isotropy of? So first, we'll talk about the model type that we focus on. In this setting, we focus only on trilingual models, just for like scope and controlledness. We use one-to-many, so like English into many target languages, because it's sort of a harder multilingual setting, which we're interested in sort of interference. And we also want to do only like 2 output languages to control for language relatedness. So here we have English translating into 2 target languages. We're actually going to fix the first target language should be Russian just to anchor something. And then we have 3 different target 2 that are all sort of different relatedness to Russian. So for example, Ukrainian here shares a script and a close family. German shares a distant family, and Chinese is completely unrelated via script and language family. And this is just sort of to see like, does sort of our representations change due to language relatedness. And then also for each trilingual model, we train 2 corresponding bilingual models. That's English to Russian. That's trained on the bytext we have available for like the specific trilingual data set, and then also English to the second target language. So in total, we have 3 different translation settings: English to Russian, Ukrainian, English to Russian and Chinese, and English to Russian and German. Okay, so the data sets that we actually use, first, we title it WMT large. This is data from the 2022 WMT general task. That's sort of just like, it used to be the news task, now it's just general. It's basically like open domain. And we do some filtering on it just for data quality. So we do language ID filtering to make sure that the bytext is actually in the language we care about. Like, you know, run a classifier to make sure the Russian data is actually Russian. And then laser filtering is basically just like making sure the bytext is actually aligned. It's actually bytext. This is an automatic filtering step as well. And we end up, I mean, depending on like the language setting, between 30 million to 90 million sentences. So this is sort of the scope we're looking at. The second data set we look at, we title multi-parallel TED. There's this data set called multi-target TED Talks, which is professional translations of English TED Talks into multiple languages. And we filter them, since it's the same TED Talks. Some of the sentences are dropped, some of them are like kept between languages, so they're not completely multi-parallel. But if you filter them properly, they can be multi-parallel. So we want the same sentences across all three of these languages, which isn't quite the case in the other ones. You might get some sentences in just English Russian and some sentences in just English to the second target, but in this one, we specifically want them all to be the same. And this setting, I mean, multi-parallel data is very interesting, but it's hard to find a lot of it. We just have around 60K to 160K sentences. And then finally, we have this data set called WMT small, where we basically subsample the WMT large data set to match the TED statistics so that we can kind of compare what scale does for us between WMT large and WMT small, and also isolate the phenomenon of multi-parallelism. Okay, and now into model details. This is just really quick, just to overview. Because we have way more data in WMT large, we use a slightly larger architecture, and for the smaller models, we're using a slightly smaller architecture. It's the IsoST architecture as defined by FAIR-seq. It has a smaller feed-forward dimension and fewer attention heads. Okay, I'll get into main results unless anyone wants to ask any questions. Okay. Do you have a question?
Yeah, so you probably said this before I came in, so if so, just don't answer. But is the idea that you're going to look at the intrinsic dimensionality of different layers with the idea that you might be able to reduce the dimensionality and get a faster model?
This is not really like.
I'm sorry, I'm just saying. They say they need a chart.
Oh,
Okay,
yeah,
it's already. Okay, maybe because it's all broken up.
Yeah. The
Sorry.
idea is just like exploratory, like a lot of people allege that bilingual models and multilingual models have different performance. They just do. Like sometimes multilingual models benefit from more sharing, sometimes they experience interference. But like our goal here is just to look beyond performance. Like, is there something different between these models and how they represent information in terms of like geometrically? Is this different? We don't really do anything in terms of like fast or different. I mean, the idea is like perhaps someone can use this, even myself, and just like make a different sort of model. Like, for example, if we find that multilingual models are, you know, using very few dimensions, like perhaps there is this sort of bottlenecking phenomenon going on. Maybe that can say that we want architectures that exhibit less sharing, especially in decoders. But in terms of speed or anything, we don't really do that. It's just sort of like we want to measure the intrinsic dimensionality to sort of see beyond just like people saying that they're like there's interference occurring, things like that. Yeah.
Okay, part of the reason I asked was that you could have like a lower dimensional manifold which is curved within the higher dimensional space.
Yeah.
And then the methods that you described here will think it's high dimensional.
Yeah.
So there are other things you could do, like, you know, run an decoder or something.
Yeah, I mean, like regarding the manifold theory, yes, there are a lot of like dimensionality reduction techniques that are nonlinear. We just focus on these linear ones for like simplicity and just like prior use and other works that look at sort of, yeah. But I mean, like I mean, the data is very high dimensional. It might be interesting to look at nonlinear techniques, but yeah, like this is just like a linear lens for now. Yeah.
Thanks.
Okay, any other questions before we get into the results? Okay, okay, I'm just gonna show the translation performance so far. It's not really like the main main thing I want to talk about, but like just to show you guys like around what's going on in these models. So basically, this is the WMT large setting, both the multilingual and bilingual scores from the trilingual model versus the bilingual counterparts. And as we can see, the multilingual models are either being matched or outperformed by the bilingual model. This is sort of known in the interference literature that in this sort of larger setting with like enough training examples, you are going to see interference, especially in the one-to-many setting. So we're just validating that we saw this as well. And in the WMT small and TED setting, the opposite is occurring, where basically the multilingual models are performing on average just like better than the bilingual models. This is also known. So we just match previous results that in a small model size with small data, you just aren't going to see interference because there's just not enough data, and additional data is just like useful to the models. But basically, we just want to say this really quick just to be like, we're not going to make any claim between geometry and interference at the moment because we're working with both an interference setting and just like a smaller setting, which is largely ignored by a lot of interference papers that say just train bigger models and you'll get more performance. Anyways, okay, to get into the actual results, one more little primer slide. I'm just going back to this original schematic to show you what we're about to compare. So here is the IsoScore or the isotropy value of the hidden states from the multilingual translation model in the decoder. And here is the isotropy value of the decoder states from the bilingual model. And we're going to compare these directly to see if there's a difference between how information is represented in the bilingual decoder versus the multilingual decoder. Okay, and here we have on the left WMT small setting and on the right WMT large setting. We'll get to TED eventually. But the blue here is the multilingual setting, and the pink here is bilingual. And each of these graphs is separated by the language setting and then again by the actual language pair. So for example, here we have English, Russian, and Chinese. On the left, we have English, Russian, and on the right, we have English, Chinese. And as you can see across basically all of these language settings and both the small scale and the large scale, the IsoScore of the multilingual models is lower than the IsoScore of the bilingual models. It's consistent across the scale, it's consistent across the language. And basically what this means is that bilingual models are using more available dimensionality to represent a specific language pair versus multilingual models. There's just less space used in the multilingual models. We're going to spend the next couple of slides looking at the same thing just to understand it better. Okay, this one is sort of the same result from a different lens. What we're doing here is we're plotting the log values of the singular values from a singular value decomposition of this set of decoder states. This is in the multilingual model only in the WMT large setting. And basically, when we're going to look at the y-axis here, which is the normalized singular value, a higher value like across the index means that more variance is captured in that dimension, sort of like similar themes as the metrics we're looking at. But basically, on the left here, we have the English-Russian language pair, and on the right here, we have the English-Chinese language pair, and we can see that the bilingual decoder singular values are like consistently higher than the multilingual decoder singular values, which means that more variance is being spread out across the dimensions, which sort of validates what we saw in the previous slide. So just to summarize this main result, for the same set of sentences, decoder states from multilingual models consistently use less available dimensionality. This is still accounting for sharing. We're not talking about like disjoint dimensions. All dimensions are being observed here, whether they're shared or not, we don't know. And also, like, perhaps this is related to the bottleneck phenomenon. We can't really say for sure, but it is like a sort of lens that one can take to sort of try to observe this phenomenon. Anyways, to continue, we can sort of ask ourselves, you know, there is this sort of like reduction in space available or being used. Why might that be? We see here that I say decoder states store language-specific information. We're going to break this down to understand what this means. So I have this equation here. It's a delta in the IsoScore. So the left value here is the language pair specific decoder states. So that's the IsoScore. Say, for example, let's isolate the English to Russian and German model. This is, for example, the IsoScore of just the decoder states for English German. And then on the right here, we have the overall decoder states. And this sort of, in that same example, is talking about the IsoScore if we use decoder states from both English Russian and English German at the same time. So like this is if you run a forward pass just on one language pair, English German, and this is if you run a forward pass on all of the languages available to your, all the language pairs available to your model, like English Russian and English German. So this sort of delta here shows what is the difference between just one specific language pair decoder state and just like on average the decoder state in your multilingual model. How much does this diverge? So we're looking at this in both the encoder of the multilingual model and the decoder of the multilingual model. So the encoder here is in orange and the decoder here is in blue. And again, we're looking at all the language pair, all the like language settings that we defined. And this is in the WMT large setting. We'll see the other ones in a second. But as we can see, the isotropy of language pair specific decoder states is higher than the isotropy of overall decoder states. So that means this delta is positive in all of these cases. Secondly, no similar pattern is seen in encoder states. That's sort of like what we see here. The orange is sort of all over the place. There's not really a consistent pattern. So what does this delta actually mean for us? And why do I say decoder states store language-specific information? So if this value, the overall decoder states, is way smaller than this value, that means this IsoScore is quite small. And we allege that some top dimensions in the decoder, like total states, are largely dictated by language information. And that's because if you have low isotropy, that means you have high variance spread only across a few dimensions. So basically, we're saying that these decoder states, which have low isotropy, have basically language information dictating some of its top dimensions. And once we separate this out by language pair specificity, we sort of remove that very high variance in those top dimensions. And we can see that by this delta being like quite large here in the blue. I have one more explanation of this in this sort of toy diagram. This is like an oversimplification. I can't say like for certainty this is actually what's occurring, but this is like an example that fits the phenomenon we're looking at. So basically, if we have target 1 and target 2 in these blobs here, these are going to be like the decoder states. We can see that if they're arranged like this dotted line here could be like principal component 1, where like a lot of variance is being explained by just like the target language, like the target language identity, or just like correlates with the target language. And if we just separate out and just isolate target 1 for a second, this looks way more locally isotropic. So basically, that's why we say that decoder states are storing a lot of language-specific information, because we can see this difference between on average and by language specificity. And just we saw WMT large has this pattern. We see also in WMT small and also TED very similar patterns emerging. In TED, something really interesting is happening where these are all quite like sharp, except for English, Russian, Ukrainian. This is like one example of some sort of like target language relatedness phenomenon we can see. Perhaps there's less language specific information to spread far apart in the decoder, but it's sort of just like isolated to this one setting and perhaps most visible due to the multi-parallel setting. Anyways, for the results, I'll go through this quickly. You might have noticed so far, we've just seen IsoScore values. I mean, it's sort of like the most well-validated in the literature, but intrinsic dimensionality is straightforward and just like has been around forever. Anyways, so all scores here are IsoScore, but the metric agreement between all values in this paper are very high. We have like R squared of 0.98, and you can see a clear correlation. So just showing that you know, in both of the metrics you want to use, they're measuring approximately the same thing, but in a different way. And also, so far, we've just been looking at final layer decoder states or encoder states, but we can kind of see like, you know, I said that there's more language specificity and the final output state of the decoder, like the things are becoming more language specific, but we just wanted to see what's sort of the behavior throughout the entire decoder, since it's sort of like the focus of our study. But anyways, this is the WMT large setting. This is looking at sort of comparing in the multilingual model, the language specific decoder states to just like the general ones, just where both of them are together. And as we can see, these blue and orange lines, which represent language specificity, are diverging from the green line more throughout the layers, which sort of means that decoder states are becoming more language specific by layer, and separating out more. Okay, so I'll just summarize quickly. So in this talk, we're studying the geometric differences between representations from comparable bilingual and multilingual translation models. And what we've seen is there's a consistent reduction in isotropy in multilingual decoder states as compared to bilingual models. And also language-specific dimensions, as we saw by our delta scores and also our layer-wise experiments, seem to occupy a notable portion of the multilingual decoder representation space, which could explain the first point. Anyways, that's all I have. There are a lot more results in the paper, but I'm happy to take any questions now. Oh, yeah, great question. Basically, it seems that there's not really like any language, like intense language specific clustering occurring in the encoder. I mean, the encoder is just modeling like conditioned English for language 1 and conditioned English for language 2. But it seems that like this can benefit from actual just like generic sharing in the one-to-many model, whereas in the decoder, it seems like the goal is just like separate out the languages and just like you know, model the language specific information, which doesn't really show like much sharing. But yeah, that's sort of how I interpret it, is just like there's not really like any sort of like conditional separation occurring, just like the English is just being modeled perhaps together for the most part. Probably. I think like some prior work has shown like some like decoder like phenomenon occurs late in the encoder. Like for example, states become more and more like interlingual looking and then suddenly just like more separate from each other, like towards the end of the encoder. And this especially occurs when you have target language prefixing in your source sentence, which is like what we use in this paper in terms of how do you do the best multilingual tokening. But I think that like helps you start conditioning for your decoder language. Yeah.
Just so I understand, so the reduction in isotropy in the decoder states is for language specific states?
Yeah, I showed results on just like language specific, like language pair specific phenomenon, but also just in general, like the bilingual model is just a language pair, and the multilingual model, if you looked at just like the language pairs together, that's going to be even lower than what you see here. But yeah, we just isolated by language pair to see like what's occurring in like the most comparable setting, like the same sentences across the two models.
Right. So do you have any like inclination or indication that maybe the different languages are occupying parts of the type space?
Yeah, I mean, that's sort of what we're trying to get at here with these like deltas and this like very toy example I'm like putting here. I mean, it's a super high dimensional space. I don't really know how many of these top K dimensions are like being used to model like language specific information. But yes, like even in really early experiments where I just like wanted to like t-SNE cluster decoder states, you can just like see a visual separation in the first couple like PCs, whatever. But yeah, it's looking like at the end of the decoder in these like one-to-many models, like at least in a few dimensions, maybe other ones not so much, things are looking quite separate, which is, in my opinion, not a good sign for sharing. Yeah.
This is suggesting that the representations from multilingual models have less informative dimensions compared to the bilingual models, right?
Yeah, that's what we're trying to say. Yeah.
And is that also case for low resource range pairs? Can you try to explain why there's a performance discrepancy between low resource range and high resource range? Based on your observation.
Yeah, I'm not sure. Like we limit things to be like completely like basically equal between the two language pairs seen in our models. Like we don't really look at like what happens when you train with like very disparate language sizes, which is like the what you see when you train real life multilingual machine translation models. So I'm not sure, but we just kind of wanted to see what's happening in this like very specific setting. Just because like we don't really know, like this is probably one of the first works that looks at just like what's going on beyond performance. But yeah, I think like there's a lot of additional work that could be done to like explain additional phenomenon, like why are low resource languages helped, why like specifically high resource languages hurt. But I guess I don't have a good answer for that right now.
Again, to clarify, we don't know that for like specific languages, these dimensions may be sideways dimensional.
Yeah, all we can see is if we separate it out, we get rid of that very high variance in the few dimensions. Yeah. Yeah, I mean, there's other work in sort of like gradient disagreement that says like in one-to-many models, there's like high gradient disagreement between like disparate language pairs in a multilingual model. This is like, I would say it's like kind of similar, just like from a different lens that like these things are separate, but yeah.
So it would really be interesting to know what the language specific information is.
Yeah.
That's being encoded in the different dimensions. And I wonder if you could get at that with some kind of probes. I don't have a particular design in mind, but I think you can come up with something.
Yeah, I mean, I've even seen previous papers try to just like add a lang ID classifier on top of your like hidden states, just like to see how many, like what is the smallest number I can reduce to in my top K dimensions. That still gives me like over 90% accuracy in lang ID. But the actual information, I'm not sure. It's sort of the multi-parallel setting is slightly confusing in this work. Like I don't really know how to interpret it completely clearly because it's so small. But I do think that you can get at more of this stuff with like multi-parallel data where you kind of just like isolate any of the other variation, except for just like language ID. But yeah, it would be interesting to know like with like more like specific like influence on like specific sentences, what's going on.
Yeah, so I guess an interesting question is whether at lower layers, these things are entangled, so that it is generalizing across languages, or if the dimensions for Arabic and the dimensions for Bulgarian are just kept separate all along, and so it's not getting generalization.
Yeah, I mean, this work is like very specific, but I think like even if you just increase the number of target languages by a little bit, you can see like more perhaps like language family things occurring, maybe, but yeah, just like would have to be in future work. Yeah.
You did look at different layers, so
oh yeah, like different layers here just shows that things are just like getting more language specific over time is what we were trying to say here.
Right.
But like in which way, not sure. Yeah.
Yeah, I also might imagine that there's less orthogonality of the languages in generative models because they have to share all the facts about the world. So you need less world knowledge to do translation because the things you're going to say are already in the source text.
Yeah, I think like purely generative models and translation models just behave differently and sort of like their like closeness to just like generation versus like closeness to classification, even though like probabilities differ in the softmax layer. But Yeah, I think one of Kenton's other master students, Chanjin, one of Kenton's master students, Chanjin, has looked at sort of similar-ish things in non-translation models. I do wonder though, but even in those sort of models, if after a certain layer, just like things are just more coexisting than really sharing. That's sort of like one of my major hypotheses, but yeah. I think things behave a little bit different in the translation setting.
Good question.